Okay, for fluid dynamics, before we get to the equations, first let me offer an overview of fluid dynamics. Fluid dynamics, it is about the movement of fluids. And depending on what type of material that we have. So here, depending on the material type, so we can have aerodynamics and fluid dynamics. And actually, for fluid dynamics, this is part of fluid mechanics in a broader sense. And for fluid dynamics, depending on the flow type, so we have two types of flows. So one is incompressible, and the other one is compressible. So these two words, actually, they are not difficult to understand. So if it's incompressible, so that means if we apply stress or pressure to the fluid, what's going to happen is that the volume of fluid will not change. So that means mathematically, it just means that rho, the density, is a constant. And if density is a constant, it also means that no matter both the temporal derivative of density or the gradient of density, both of them should be zero, because density does not change with no matter time or spatial coordinates. And if we take a look at the REV, we will find that the movement of fluids here will involve two major physical processes. And the first one is the conservation of mass. And the second one is the conservation of momentum. So in the following, I will show you how to get the governing equations for the conservation of mass and the conservation of momentum. So first, let's take a look at the conservation of mass. So this one is a little bit simpler to understand, than the conservation of momentum. So this is a conservation problem. So we talked about this type of problem before we started talking about heat transfer. So it's the same thing. And for this type of problem, what is the first thing that we need to do to derive the equation? Find out the conserved quantity, right? So in this case, the first we need to find out the quantity to be conserved. Quantity to be conserved. And the quantity to be conserved in this case is mass. But since we are talking about a REV, so we are talking about unit volume. So here it's not mass, it's specific mass. For specific mass, it's just the mass over specific means per volume. Here is m over v. So you will find that the quantity to be conserved in the conservation of mass for our governing equation here is just density or unit mass. So with this, get this one, then we can just recall the general conservation equation. So any of you still remember the equation of conservation? We have an accumulation term. We also have a advection term. Source and also flux through the boundary, right? Yeah. So we should have 4 of them. So what is the accumulation term? Any of you still remember? So that's the change of the quantity to be conserved with respect to time. You just got it. So it's here, let's use, for general equation, so let's use U. So U could be a scalar and it could be so here we're talking about the general equation. So it's partial U, partial T. This is the accumulation, right? What about the advection term? Any of you still remember? So advection is cause. What's the cause of advection? Yeah, velocity. You got it. So that means we should have a velocity, right? And also we should have the quantity to be conserved. So actually, this term is just the divergence of v, then times u. Right? The second term, advection, and previously, we also have 2 other terms. We have that flux through the boundary, right? And we also have source, right? Or we use different terms. We use G or some other term for source. Anyway, but here in fluid movement, actually, for the conservation of mass in the fluid dynamics, we can consider these things. Consider, this flux. Consider this G, but they're not very common. So usually we just need to consider, because usually we don't have sources or sinks for mass unless we have a pump or something. But let's assume that this is a special condition, so we don't consider that a special condition there. This is the general equation. This is general. So we want to derive the equation specific to water movement. Then we just need to replace the U with the quantity to be conserved. So what is the quantity to be conserved again for mass conservation? Density, right? So just replace U with rho. Partial T plus the divergence of V rho equals 0. This is specific. To water movement or fluid movement. And I mentioned that, this is the general, but, it's still general, but it's not as general as this general. And then for this general mass conservation equation for fluid movement, we have a special case. That is when the liquid is incompressible, or the flow. So if it's incompressible, then what's going to happen? If this is 0, that means rho partial t is 0, and also this one equals this one, right? So eventually, we can get the equation, this equation. So if it's incompressible, we only have a very, very simple equation. So many people also call, no matter, this equation, or, the above one, general one for the mass conservation in fluid movement, they call it a continuity equation. It's the same thing. So this is for mass conservation. Let's take a look at momentum. Momentum is more complicated. So let's do the conservation of momentum. So we're going to do it in the same way. We believe that incompressible fluid is just a special case of compressible fluid. So first we're going to generate the general equation, general momentum conservation equation for compressible fluid first. Then we will simplify that equation to get a simpler equation for incompressible fluid. Momentum. And we follow exactly the same procedure. So first step, we need to find out the quantity to be conserved. So take a guess. So what is the quantity to be conserved for momentum? Think about it. And for mass, we have specific mass. What about for momentum? Yeah, momentum per unit of volume, that's it. What is momentum again? You guys still remember? This is high school physics, right? So what's the equation for momentum? What's the definition of it? If my mass is m, my velocity is v, what is my momentum if I move? It's specific momentum. So momentum is mv, right? Then per unit volume, we use capital letter V. So what are we going to have? Rho v, right? So this is rho v is the quantity to be conserved, in water movement. So then we recall the equation of conservation again. So we recall this equation again, the general equation. But now we should replace u with rho v, right? So if we do that, we're going to get the equation like this. But, sorry, for momentum, this one is not a zero anymore. We're going to have some other things. So we will have stress. And in our case, we have F. This is the body force. Let's put right down F as a final term. And we also have the convergence of sigma. So this one may look similar to what we did in the mechanical field. It's just like F equals ma. Can you guys understand this? But this equation still look complicated. So you can see that here. You have it's the partial derivative of two term, and and here is the partial derivative of 3. And here, there's nothing between the two v. That means it's a what type of product? Tensor, right? If there's a dot, that's a vector product. Yeah. But there's nothing between them, so tensor product. So a scalar, it's a vector, we're going to get a second order tensor, right? Yeah. And you can also take a look to see if this equation is correct by checking the order of tensors on two sides of the equation. Here, this is the vector, so everything should be a vector, right? Vector, the temporal derivative of a vector should be a vector, and here, vectors, put them together, should be a second order tensor. And then you have a divergence here, where we reduce order by 1, so we get a vector. Yeah. And here, this is the tensor, divergence of tensor, we get a vector, right? So everything is a vector. That means we're good. But no, if we split this equation, this is too complicated. We wanted to reformulate it. So if we do it, we can get a pretty complicated equation like this. So you can do it based on what we learned for tensor analysis, based on the rules for different operators between tensors and scalars. So you can try it yourself. You should be able to derive this equation yourself. You take some time. So we only change the left-hand side, the right-hand side, we have the same thing. And this actually is just this. So if you don't know why, take a look at those identities that I offered. I offered many equations for the identities in tensor analysis, and this is one of them. So the divergence of these two was split into two. The product of two was split into two terms, and this is 0. That means the first this whole term is 0. So the whole term is 0. Then finally, we can get the whole thing is 0. So we can simplify the equation, and we get rho partial v partial t plus v dot product. The gradient of v equals the divergence of stress plus f. And some people, they prefer to use simply to write this equation in a different way. They say that, this should be, they use a capital letter D to represent a different type of derivative. Again, you can see that if you use this one, this is more like MA, or this is MdV dt equals F, right? Let's get rid of this one to avoid confusion. So this is what we learned in high school, and this is what we are doing today. And this type of D, so D is a new operator. So D is an operator, is a combination of these two. And this operator is called a material derivative. So okay, so now we already got what we need. So this is the equation, conservation equation for fluid measurement, for fluid movement. But you can see that, we know that the dependent variable of this equation is V, is the velocity of the fluid. However, we have V here. Rho is the material property, so we know it for any problem. But here we have F. F is the body force. Usually, if we know the problem, we can get it. Usually, this one is for example, it could be caused by gravity or any type of magnetic forces. So gravity, magnetic forces. If it is gravity, what's it gonna look like? What's gonna happen if it's gravity? It is a vector, right? Yeah. So it has 3 directions. For gravity, what's gonna happen? We only have value along. Let's say that if z direction is vertical direction, we only have value along that direction, right? So it's gonna be like something like x0, y0, and z direction should be rho g. So the gravity depends on the density, the unit weight, right? So unit weight is density times the gravity constant, rho g. So it is a vector. And now the problem is that we don't know this thing. So what is the stress in fluid? In solid, we know how to deal with sigma, right? We do that based on a few things. First we want to connect stress to strain based on the constitutive relationship. And then we connect strain to deformation. And then this deformation or displacement U is dependent variable. So in that way, we connect sigma to the dependent variable. Here, we want to do it in the same way. We want to connect this one to V, so that we only have one unknown, one dependent variable in one equation. We don't have 2 unknowns in one equation. In that case, we cannot solve it. So to do this, but it's different. Now it's different. We cannot do it in exactly the same way like what we did in solid. However, the procedure that we're going to use is not exactly the same thing, but it's not much different. So to do that, in fluids, usually we do it in this way. So again, sigma, second order tensor, it has the same shape. So sigma xx, sigma xy, sigma xz, sigma yx, sigma yy, and sigma yz, sigma zx, sigma zy, and sigma zz. So then what we're going to do is that usually we wanted to split this term into 2. The reason is split into 2, and one is the mean part, or hydrostatic part. The other one is the deviatoric part. So for the mean direction, we use sigma m. So sigma m, so I'm going to do it later. Sigma m and all the other terms, they're just 0, 0, 0, and a plus sigma xx minus sigma m, and then sigma yx, this is sigma xy, sigma xz, and sigma yy minus sigma m, sigma yz, sigma zx, sigma zy, and sigma zz minus sigma m. So in this way, we have a mean or normal, mean or hydrostatic, or normal. And this part is deviatoric, for the shear part. So we divided it into two. And m, sigma m, is just the mean of sigma, the three normal stresses. So it's the mean of sigma x plus sigma y plus sigma z. P is just, pressure. For pressure, the big meaning of pressure for water is like, for water, has the same pressure along all the directions, right? So it's similar to this thing, this mean stress, mean normal stress. But there's a difference. For P, we said that is positive when it's a compressive stress, right? You have compression, it's P. But if we have tension, it's no. But actually in fluid, we don't have tension. So in bulk, at least in bulk fluids, we don't have tension. So P is the negative of sigma m. So then, because of that, now we can write it in the same way. So sigma should be the negative of P plus sigma xx plus P sigma xy sigma xz sigma yx sigma yy plus P and sigma yz and sigma zx sigma zy and sigma zz plus P. And if we want to write this equation using the tensor notation, what is it going to look like? It's going to be negative P times, we need to use a unit matrix, right? This one or this one. Kronecker delta. You guys still remember this one? It's just like 1, 1, 1, right? It's 1, 1, 1. You use something like this. So, and then plus, so for this deviatoric part, we give it we use a different symbol to represent it. We use tau, but it is a matrix, so second order tensor. So we put a bar above it. Now with this one, you may be confused a little bit. You said that, no, originally we only have one sigma. Now you split it into two terms. You are making it more and more complicated. It's true, but as I mentioned, there's a reason, because fluid, responds to stress in different ways along different directions. Along normal and shear directions, they are different. So because of that, it's necessary to split it into two terms. And then with these two terms, next thing that we want to do for P, water pressure, we don't need to worry about it. But for tau, we want to connect it to something that we know. And in this equation, what do we know? In the Gaussian equation for momentum transfer, the dependent variable is what we need to calculate, right? So it's okay, if we can connect sigma tau to V. And actually, we can do it in this way. And so when you are at high school, were at high school, you possibly have learned one thing. So that thing is that's a very simple experiment. This was observed by Newton. It's just like, when we have two plates and we have liquid, for example, we have water between two plates. If we try to shear the two plates, make them move relative to each other, we can observe one thing. That is if we shear it, you will feel that there's resistance, right, between two plates. And the resistance, that's kind of shearing stress. That shearing stress is proportional to the velocity of the relative movement, right? And it also proportional to the distance between the two plates. So it's proportional to V over distance. So that's like a gradient, right? So this is how we observe, that's kind of all the way begin. That's the beginning of deriving a formulation for the relationship between tau and v. So by extending, this simple thing that we learned at high school, we can get another thing, that is tau is proportional to, so the deviatoric stress, the shear stress between the two plates is proportional to the gradient of velocity. That's u over the distance between the two plates. So and the proportionality constant, we used mu. That's the viscosity. So it's like so this is the extension of the definition of viscosity. And this one is the kinematic viscosity. That's the definition of it. So does this equation appears familiar to you? Have we ever did anything similar to this equation before? The gradient of v and this is the transpose of the gradient of v. Have you ever seen anything like this before? Stress, right? That is the displacement stream relationship, right? We said that stream is defined as 1/2 of the summation of the gradient of displacement and the transpose of the gradient of displacement, right? And then if we connect it to stress, we know that stress is proportional to strain. So it's similar here. You can see that here you can understand that if there's nothing here, if you only have this is more like a strain rate. It's the change of strain with respect to time. And here this is like a material property. So we times this one with the strain, we get a stress. So it's similar. But we still need to keep extending this one. This one is a direct extension of the experiment, the shear force between two plates, the one that I just mentioned before. It's an extension of it. But some people found that the deviatoric stress is not only proportional to the shear strain rate, it's also proportional to the volumetric term. There are multiple different formulations, but the simplest one and possibly the most widely accepted one is this one. And this one is the constitutive relationship for fluid. And you will see that this is the shear part, and to be more specific, is the shear stream rate. Can you guys understand why it's here? I put a rate here. What's the meaning of rate? Time, right? You have a rate because here v, we can believe that is kind of, is the temporal derivative u with respect to time, right? The change of location with respect to time. That could be the definition of velocity. So in mechanical field, we talk about the gradient of u, so that's a stream. And here we talk about the gradient of v, so we have one more derivative with respect to time, so it's a rate. We add a rate here. And here, the second term, it is the volumetric strain rate. Then, with this, we just substitute this constitutive relationship back into that general equation that we derived for the momentum conservation in fluid movement. So we substitute this equation to here. Then we can get the momentum conservation equation for fluid movement. So if we do that, we will get the following thing. That is rho should be B, apologize. This is the equation that we can get, by substituting the constitutive relationship into that the momentum conservation equation, and we can continue to simplify this equation, and we can get this equation actually can be simplified as oh, you mean here F is missing? Yeah, here. We can add F here. And this term, I mentioned this before, is the identity. It equals this. So we have then plus, so just copy this term. Should be V. Then minus 2/3. So for this one, we can get another identity. So we will get
that part, 2/3 part should be in that divergence parentheses, right?
Okay, with this one, now, so you can get the meaning of everything. Accumulation, right? And this one, advection. And this one is the pressure, water pressure, or the normal part. And this one is shear. And this one is also shear. It's a shear caused by strain. Let's get it in this way. It's a shear normal or volume. And this one is the body force. So you can see that it's long, but every term has a clear physical meaning. And we can derive this equation all the way from the original equation. So there's no secrets, there's no but the thing is that if you try to read a book or even take a course, you will find that for this part it could be really complicated. However, if we just focus on the major part, we will find that it's not that complicated. The equation is still long, but it's not difficult to understand. And then this is the general equation, but we still want to further simplify this equation. I want to make another change. So that, because this is for compressible fluid, I want to derive an equation for incompressible fluid. So let's copy everything until we get this term. Does this term look familiar to you? Have you ever seen anything like this before? The divergence of the gradient of something and the transport of the gradient of something. Stress-strain relationship, right? We did this one when we are doing that. When we are deriving the Navier's equation, the governing equation for mechanical field. And I use index notation to show you guys how to derive the equation, right? So here I will not repeat this deduction process anymore, but instead I will just offer the conclusion directly. So this term was split into two terms. So it becomes mu, the Laplacian of V, and mu, the gradient of divergence of V. So one term splits into two. And then the other things, we just copy it. Okay, this is the general equation for incompressible fluid. For compressible. So actually this one is also the general equation, but they're just in different, just show the equation using different formulations. So what's going to happen if it is incompressible? So can you guys derive the equation? So if we go back to here, the divergence of V is zero, right? So here, do we have the divergence of V? So how many terms has the divergence of V? 2, right? This one has a divergence of V. This one also have a divergence of V, right? If it's incompressible, these two terms should be 0, right? So incompressible, then we're going to have the following equation. You're going to need two equations, for fluid dynamics. You will need both. Where is the momentum balance? Yeah, this one. So this is the first equation, and this one is the second equation. So you're going to need two equations. So combine them, we give them a name, called Navier-Stokes equation. So these are the Navier-Stokes equations. They're not just one equation, they're called equations. So, but if it's incompressible, you're going to need to use this equation, and we also have a incompressible version for the conservation of mass.
I think I'm falling for you.